Hello, everyone, again. I saw some of you just a minute ago, or just a few seconds ago. But if you haven't been watching, where have you been? So first off, I want to say thank you to all of our sponsors who make CumCon possible. Our virtual editions are completely and utterly free of charge, and you don't even need to register. So thank you very much to them. I'm not going to... Actually, no, I'm going to go through all of them right now because they all deserve their spotlight. So first off, we've got our platinum sponsors, Subspace, Daily, Element, and Mux. They all help make this whole thing happen at the very beginning. Then we've got our gold sponsors, Taloo, 100 Milliseconds, and Dite. Taloo have sponsored absolutely every single CumCon there has been. This is our fourth, and they've sponsored us every single time, and just wanted to help. So thank you very much, especially to Taloo. Silver sponsors, Loway, Sangoma, Millicast, and webRTC Ventures. We've got Jambones, Telecurve, and Panton as our community sponsors, and then we've got all of our AV partners who are physically making all of this happen. So we've got PSP, the AV team, Millicast, Broadcaster, Subspace, Element, Mux, and Meet Echo. Meet Echo made the plugin that makes Broadcaster VC work. And so special thanks to them. So first up, our session now is from Tim Panton, and he's going to talk to us about Whip. So I'm just going to pass you over to Tim, and then hopefully we'll have some time for some Q&A afterwards. So I'll see all of you when Tim is done. Take it away, Tim.
About writing a new open source WebRTC stack in a week. And kind of the subject matter of that is Whip. So I've ended up writing a Whippy, which is an open source Whip client that runs on a Raspberry Pi. So a little bit about me. I'm the CTO at Pipe. I'm Tim Panton. Pipe licenses a lightweight clean room WebRTC implementation for IoT devices. I've got a bunch of history back in telephony, but also some history in security. But as I say, these days I write software at Pipe. But I also spent some time in the WebRTC world in terms of setting standards, helping set standards at the W3C and the IETF. And that's kind of how I got into this problem. I rather foolishly a few months ago said, yeah, sure, I'll do a Whip implementation for the IETF hackathon, without really thinking about what that meant. So it's worth talking a little bit about what Whip is. Hopefully you'll go and watch Lorenzo's talk and some other talks about what Whip is. So I'm not going to kind of talk much, but I think you need to know the very basics for this story to make any kind of sense. So it's a draft standard of the IETF. Well, it's not at that level, but it's heading that way. And the idea is it's a protocol to let you use WebRTC for broadcasts, essentially. And the idea is to replace the RTMP ingest, which is typically used by people like Twitch and YouTube and Facebook Live and those sorts of folks, with something based on WebRTC, which has got lower bandwidth, lower latency, better bandwidth estimation, and a bunch of other nice properties which are ideal for broadcast, but that RTMP don't have. But it's been seen as being too complex. So the idea with Whip is to take out some of that complexity. The diagram I shamelessly stole from Lorenzo's talk, and also you can find it on his blog. So I strongly encourage you to go and read that there. But my goal in this, my aim in this was to try and see if we could test whether Whip was possible on small devices. Because if you look at the ecosystem for RTMP, there are small devices, typically called encoders, that generate data from cameras and send them up to broadcast devices and streaming devices and whatever. So we need to be able to test that Whip can do that on small dedicated hardware. So I thought, well, what I would build would be effectively a Whip cam. Again, it's somewhat foolish of me to think of doing this, but I thought I would, so hey. So the obvious thing to do that was just to use the pipe stack. I mean, I got a webRTC stack that was aimed at small devices, so why not just use that? And it turns out that's actually quite tricky because of the assumptions that pipe makes and the goals that pipe has. It's difficult to use it for Whip. So, I mean, yes, they're both based on webRTC, so that's a good start. But if you look at the way that pipe uses the data channel, for example, it actually requires a data channel in order to say what this discussion is, what this usage is about. So it actually actively requires a labeled data channel. Whereas Whip just doesn't do that, because Whip is a single purpose protocol and there's no kind of discussion about what it is that this thing is. It's not whether it's a baby monitor or not. It's just a webcam. That's all single purpose. And likewise, the security is kind of done totally differently. On Pipe, we're very much edge-based. We hold the keys and we do the auth all at the edges. The devices maintain their own security and their own associations. Whereas with Whip, it's very centralized. You've got WebAuth and bearer tokens, and that's the kind of style of security there. And likewise, and that sort of leads on to the architecture, whereas Pipe's very much P2P. It's like between your smartphone and your baby monitor, whereas Whip is very much client-server. You've got a big service like YouTube or whatever, Millicast, and then you've got a device on the edge that's talking into that as a client-server relationship. So it's a totally different fit. And that basically meant that I was when I was looking at doing this pipe, I realized I was going to have to disable all the security in order to do Whip. And the more I looked at that, the less I liked it. So then I thought to myself, well, I've written 2 special purpose webRTC stacks already. Why not just do a third? Which leads us to kind of what is webRTC? Well, I mean, there's a vicious quote here, which isn't too far from being true, that basically it's a bunch of reused specs glued together. And these things all pre-existed webRTC. So, UDP, stun, turn, ICE, and they're all just strung together to make an overall structure. And it's done in a reasonably logical way so that, the interfaces are reasonably clear. Unfortunately, I've missed out one standard, pre-existing standard that's in webRTC, which even more unfortunately isn't neatly structured in the same way that the others are. It has its fingers in absolutely everything. The SDP gets absolutely everywhere throughout the stack, unfortunately. So what do you need to implement Whip? How much of that do you need to implement Whip? Well, the good news is that actually you don't need the data channel at all. And you can get away with a lot less SDP. So we've simplified this thing quite a lot down to being stun and ice. You don't have to have turn, actually. You can do Whip without turn. You need SRTP, you need DTLS, you need Opus, you need H.264. And the good news is that all of those things are available as open source libraries. Actually, they're available in multiple different languages as open source libraries. So you can pick your own language and just glue them together. How hard could that be? I mean, you're just gluing a few open source libraries together. So in order to make that actually achievable, it's really well worth picking libraries that you trust, because you're effectively trusting the maintainer. With some environments, some languages, that trust is even greater than in others, but essentially you're trusting the maintainer with your customers, which is kind of scary. So you need to choose libraries that you know and trust. And I'm going to confess to having used Java for this. I tend to use Java as a default, but the main reason for that is that it's memory and type safe. Like, I have a security background, which makes me very keen on having things that are languages that are memory safe and type safe. On the other hand, it's also super efficient on small processors because it's got a long history back in that space. So we can get stuff done on small devices pretty efficiently. And again, because of its long history, there's a ton of open source libraries out there. But for those of you who probably last did Java in college, and it was kind of Oracle Java 6, OpenJDK11 is not the same thing. It's not the same beast. There are a lot of new, much nicer idioms that you're allowed to use in JDK11. And there's some fantastic tooling out there that will do some really cool stuff in terms of like the way the IDEs work and stuff like that. And finally, not desperately relevantly to Whip, although slightly, there's JavaFX, which is really nice. So what we ended up with was Whippy, which is an implementation of Whip for the Raspberry Pi. It takes all the available Whip shortcuts that we can find. So we take minimal SDP. And the key thing there is that it's not a negotiation. Classic SDP is a negotiation. You're back and forth about, whoa, I could do this and you could do that and da, da, da. Well, this is much more like a ransom note. You know, the offer is a statement of intent. This is the encoder saying, this is what I'm going to do. Like it or lump it. And strictly the Whip standard says that if the server doesn't like it, it should send back, I think it's 300. So it only sends a 200, 201 status back if it likes the SDP you've given it. So I chose not to do trickle ice. I chose not to do turn. For my particular use case, that's fine. Other cases you might not want to. You might need to include those. It does passive DTLS, so half the DTLS stack. I don't have to implement the DTS plan. I can force Whip to stick with passive DTLS, which is great. And I assume only one audio and one video track, and I assume fixed codec. So there's like really nothing to negotiate. This is the deal. And that lets me do this really nice thing, which is to basically layer the stack as a very thin shim on top of the audio and video hardware, so that you're assuming that the camera hardware is capable of doing H.264 encoding in hardware, and so you really don't have to do anything to do that in software. And that means that you get minimal external dependencies, no JNI, no GStream, no FFmpeg, no AV codec. It's just like straight to the metal. So now I'm going to do a code walkthrough. If I can find my correct screen and see what I'm doing. So with any luck, what you're seeing now is my IDE, slightly larger font than usual, but my IDE. And what you've got here is the basically classes to glue the main protocols into the Whippy. So you've got a DTLS class, which acts as a shim onto the DTLS implementation. You've got the ICE class, which acts as a shim onto the ICE, and likewise for RTP. And then you've got Whippy, which kind of glues them all together. So it's actually a pretty simple way of looking at things. So basically what we're doing here is we create an instance of ICE, we create an instance of DTLS, and we create an instance of RTP. And then we start the ICE gathering IP addresses. And once it's got them, it will call this onGathered feedback callback. Now, this is an interesting thing here. It's something you couldn't do in Java 6 and you can do in Java 11, which is these are anonymous inner classes. Now, that has a really nice property, which I'll show you in a second. So once the thing has gathered, once we've gathered enough IP addresses, we can just go off and make an offer. So we've got enough information now. Once we've gathered the candidates, we've got enough information to create an offer, and then we can send the offer, and we get an answer back, which we parse. And from the parsed offer, we only need, well, we need kind of 4.5 things. We want to check that like everyone's in agreement on how many media streams we're running. Like we want one audio and one video. So we need to check that that matches. And then we need the UFrag and the UPass for ICE, and we need to get the candidates. And we also need to get the DTLS fingerprint. So those are the only things we need out of the answer. So out of the answer, which might be like 50 lines or something, we only actually care about 4 things. And once we've got those, we can do connect. Now, this is what I was saying about the anonymous inner class. What we've got here is within this method, we've got this, we can access both the scope variables that are in scope for the outer Whippy class, which is this FFP variable, for example, and we can also access methods and variables from the inner ICE class. So this environment here has access to both of those scopes, which is really nice way of doing glue. It's a good way of encapsulating glue between two different protocols without like having to entangle them too much. So anyway, once we've connected, we get the on-connected callback, which we then use to set up how that connection is forwarded on to the other protocols. So when we get an RTP packet in on ICE, we pass it to the RTP. And when we get a DTLS packet in, we pass it to the DTLS engine. Now, the DTLS library is assuming that it's talking to an actual datagram socket, which it isn't. So we have to fake up a datagram socket, which is what this candidate transport does. So there's a little bit of faffing about there to make it look like it's real. And then we start DTLS. DTLS goes off, does its thing, does its handshake, and then comes back. And once it's complete, we can extract the cryptographic properties from that handshake, push them into the RTP engine and tell the RTP engine to start. And then the RTP engine is sending these SSRCs with these p-types. I'll just do a very quick glimpse into the RTP side because it's actually really nice. Basically, we take an ICE-aware SRTP implementation, give it the cryptographic properties and the types and the source SSRC, and then we just connect it, in this case, to dev video. So dev video on Linux, in this particular instance, if you configure it right, is sending H.264. So we just parse that and then send it into, packetize it and send out the packets. And pretty much the same thing happens with the audio. We create an ALSA aware thing, and then we feed it to SRTP protocol implementation, and boom, we're sending audio. And so those two things are kind of actually relatively simple. And then the final thing here is that there's a bunch of classes that implement some of those things that we talked about, like the offer answer and the ALSA and the H.264, and that are layered on top of those open source libraries. But you can see we've got like, what is it, 9 classes to implement the entire protocol. So I'm going to abandon this and go back to our presentation with any luck. So what did we just see? Well, we saw Whippy. The source code's available on GitHub as pipe Whippy. It's GPL. It currently assumes Raspberry Pi hardware. It could support other hardware. You basically just need something that's got a H.264 encoder that's supported by v4L2. And that's pretty much all, and a Java 11 implementation. So, it's perfectly possible to port it, and I'd really love it if people either send me the hardware to port it to or port it themselves better. It's missing a bunch of features as compared to the pipe stack. I mean, like the security model is completely different. There's a bunch of things it's no idea how to do the pipe stack does, so it's kind of different animal. But it does work. It does do the task. I'd really encourage you to send issues, PRs, forks, whatever, to the GitHub. It would be wonderful if you would do that. So coming back to the hackathon, what happened? Well, we tested Whippy against 3 Whip servers. The Millicast content distribution service. I had to tweak the STP CNAME slightly, but otherwise it worked. Ghislaine, which is a video conferencing server, I had to tweak the STP again to get the mids different, but like that was pretty minor. And the Janus broadcaster, if I remember, it just worked, which is cool. So, and I tested it on both Raspberry Pi 3 and 4 with a couple of different PiCams. So what have we learned from this? Well, we've answered the question that I started out with, which is, does Whip work on small devices? The answer is yes. We I've learned, and I think this is a subtler point, which is really interesting, which is that we've learned that WebRTC is still extending its reach. It's reaching out from the kind of video conferencing place where it started and the telephony place where it started out into adjacent domains like broadcast, and in my case, like baby monitors and stuff like that, IoT. And I think one of the things that's most interesting about that is that I think we're going to see an increase in small dedicated hardware that meets those goals. And so that's our kind of big learning. And I think to enable that is this sort of subsidiary learning, which is that there's more than one WebRTC stack, right? You should pick the WebRTC stack that does the right things for your environment. And it's probably increasingly not libWebRTC. LibWebRTC is very happy in the browser, but like in a lot of other places, it's deeply uncomfortable. And what's more, what we proved is that if there isn't a WebRTC stack out there that does exactly what you want, it's possible to build one. You can build a WebRTC, single-purpose WebRTC stack in a reasonable time frame, provided, of course, that you know what you're doing, you know what you want, which is actually sometimes harder, and that you can find a bunch of open source libraries that will do what you need there. So there's a little bonus here, which is that because we're using Java, we've got JavaFX available to us. Now, JavaFX is a graphical interface, kind of spiritually derived, I think, from Flash. It's the sort of Java take on Flash. So where you can do really pretty visual graphics, actually in process, running inside the process without having to fire up an enormous 5 gigabyte Electron image. So what I've done with Whippy is to layer on top of Whippy a graphical user interface that shows us the statistics for the current upload. So the current upload. So in this screenshot that you've got, and that actually runs on the Pi. So this screenshot you've got here, we've got, you can see that I had, I don't know, just over 0.5 megabit per second spare. So the available bandwidth was higher by a bit more than 0.5 megabit than the used bandwidth. I wasn't getting any packet loss. You know, they were getting 50 packets a second on the audio and 30 frames a second or whatever. So you could actually see what was going on. So it was really nice for dedicated devices, camera folks, that sort of thing. So that's the kind of added bonus for that. So at this point, I would normally do a demo, but it turns out that actually the whole thing has been a demo because that is running Whip. This is a Whippy upload to Broadcaster using Whippy on a Raspberry Pi 4, somewhere down there, on a PiCam, running live into Broadcaster. So yeah, there you go. That's what standards do for you. And I would very much welcome any questions if we still have time. And otherwise, you can contact me by email. Take a look at the Pipe web and blog. There should be stuff on there that's of interest. Tweet at us on Pipe IoT. Or, as I said, I'm really keen that people put stuff onto the GitHub, issues, whatever, both for the Whippy project, but also for some of our other Pipe open source. That would be wonderful. And yeah, great to have some questions. Back to you, Dan.
What an interesting session that was. I mean, Whip is going to change the way that we do stuff when it comes to broadcast media, and being able to include WebRTC into that very simply. So let me bring Tim on so he can say hello. And hello, Tim. How are you?
Hey, Dan. I'm good. It's rainy, but I'm good.
Good. So I think the most powerful thing of that talk was, look, we've been using Whip all along, and and that's a powerful statement. So what's coming next when it comes to Whip, as far as you're concerned? What do
I
you see
think
as
that
the next thing?
the really fun thing, or the part of the reason why I did this, is whipping cameras. I think the idea that you could get something like a kind of GoPro or one of these little steerable cameras, and you send it out to the person who's going to do the broadcast for you, and you send it out to them a couple of days before, but you can remotely control it, you can steer it, you can focus it, and and you don't have to care about what their internet is, because like if they've got like halfway decent internet, WebRTC will get a decent signal through. It'll do with all the NAT, it'll do with all that, and you don't have to worry about their laptop and their camera and all of the rest of it. It'll just do it. If you got really paranoid, you could just send it with a 5G module in and like not care about any of it. So I think that is really exciting. The idea of taking WebRTC out of the laptop, and obviously I'm way biased on this, but taking it out of the laptop and putting it into smaller devices that you can start to afford to ship. I mean, that Raspberry Pi, I don't know, even with a decent camera on it, it's still only like 60 quid or something. So you could actually afford to not get them back.
We all remember well, maybe we don't all remember. I'm very much biased, but last year, like at the Golden Globes, like they'd send out these like suitcase packs with like a laptop and a camera, and like they were self-running packs, but like there was so much involved with getting that picture back for virtual Golden Globes or whatever it was, and to think that could just be replaced with a Raspberry Pi with a nice camera module on it, is pretty nifty.
I think, that's also the other thing that I wanted to kind of get over in this, is that WebRTC is evolving out into niches that it hasn't been in. Like, we're all used to it doing all the web conferencing stuff, and thank God it has been, because it's been a lifesaver for a lot of us. But I think we're starting to see it move out into edgy devices, smaller devices, and other business areas. And I think, broadcast is another example. It's like, it isn't a video conference. It's the same underlying protocol, but the business case is completely different. And I think that's really exciting to see WebRTC spreading out into different devices and different places. And for me, that means you do need a different stack. You can run the same protocol, but the optimizations are completely different. And that was part of the fun about doing this one-off single-use stack. It's like I could make a huge set of different optimizations because I knew things about what we would and wouldn't be doing.
Right. Take you don't have to deal with all of the stuff that libWebRTC has to deal with, because there's so many unknowns, and you can just concentrate on X and Y and Z, because you know what hardware or whatever it's gonna end up talking to.
Yeah, I mean, prime example for that is the H.264. Like, it only does, that particular piece of code only does H.264. It knows it's always going to do H.264, and it knows it's always going to do it with a particular hardware encoder on a particular Linux interface. And so, like, there's a huge swathe of code in libWebRTC dealing with all the possible encoders and all the modes it could be in and all of that. And with this, I don't have to do any of that. I know exactly what mode we're going to be in. I know exactly what the encoder is, and we're done. It's like 4 lines of code. So it just simplifies all of that and cuts out a lot of latency as well. So it's kind of weird optimization in 2 directions, which is great.
Sweet. Thank you so much for joining us. We shall be back for another session later on. And thank you very much, Tim. And goodbye. See you soon.
Goodbye. Great to see you.